Go. Hello. Hello, Mr. Ryan, alright? Yeah. So today we're given a square metric. Square metric, you know the square metric. And square metric, yeah. For example, this is the square metric of 3 times 3. And we want to find out if each row, each column contains all the numbers from 1 to n. No. Not quite similar. Yeah, Sudoku, but no, 1 to n. For example, this is n equals 3. 3 times 3, so this 1, 2, 3, 3, 1, 2, 2, 3, 1. Then that's okay. Why is that?
Because there's 1, 2, 3, there's 3, 1, 2, there's 2, 3, 1, there's 1, 3, 2, there's 2, 1, 3, there's 3.
Yeah, exactly. So each row contains all the numbers from 1 to n, 1 to 3. Each column contains all the numbers from 1 to 3. Okay, this is one. How about if I give another example? 1, 2, 3, 1, 3, 2, 2, 2, 1, 1. Is it?
No, because on the column, the first column is...
Yeah, this one. Yeah, and then this one. Okay? Yeah, easy. Yeah, today's task. Easy. What's the idea?
You have to find all of the ones in a row like that.
No, not necessarily the diagonals. Just the rows and columns. But that's a very good point, yeah? Rows and columns. Rows, columns. Contain 1 to n. Okay? Yeah? So, any idea we're solving this week? So, I mean, this problem is easy. We just go through each row to check if each row contains all the numbers 1 to n. We go through each column to check if each column contains 1 to n, right? Yeah? So, look, we are checking the numbers. So we are not checking the sequence, right? We're not checking the order. Sequence doesn't matter. But what matters is what? The numbers. So if we want to compare two lists have a same, like 1, 3, 2 or 1, 2, 3. Yeah, these are the variants of the permutation. Yeah, but they are using the same numbers. So what kind of data structure can you use? To compare, these are all equal because what? Because they all contain the same numbers from 1 to 3, right? Yeah. So what kind of data structure can we use to compare? If we turning into these three into something, something.
That is false. It's false.
I'm saying this A is a list, B is the list, C is the list. And we want to find out if all those three lists contains the same number of items, same numbers, right? So they should be equal because they all contain 1, 2, 3, but different order. So we want to convert it. How do we check this? We can convert it to some kind of 3 letters here, and then we can compare if these is the same. Any idea? What kind of data structure have you learned so far?
Matrix.
I mean,
Zip.
No. What kind of data structure? I mean, the first one is S. The second letter.
Exclusive.
So S what?
Set.
Yeah, set.
I just said set.
Yeah. So we're converting these to set. Yeah. Then we can compare if the numbers are equal, right? Yeah. The set is a very useful data structure. The set contains unique. Okay, because we know these are 1 to n only, right? So they contain the unique numbers. Then we can compare if they contain the unique numbers, right? Right? Yeah. Okay, so the other thing I want to look, it's easy to go through the rows, right? We just say for R in metric, and then you give us if this is M, okay? Then we say for row in M. So this row will contain 1, 2, 3. 3, 1, 2, 2, 3, 1, yeah? That's easy to compare the rows. How about the columns? Columns is not easy, right? But in Python, we have this. We can use this zip. What's zip? Remember? What's zip?
No, just said zip.
Zip. What's zip?
A zip is a zip.
Yeah, you put two things together, yeah? Remember, look. This is 1, 2, 3, A. equals that. B equals what? 4, 5, 6. And what's JIP AB?
1, 2, 3, 4, 5, 6.
What's JIP AB? Come on.
1, 2, 3, 4, 5, 6.
Not quite. Look, what's JIP? Look. This is A. This is B.
1, 2, 3, 4, 5, 6.
Look, this is
1, 4, 2, 5, 6.
yeah. Look, so look, this is the jipping. Yeah, you just imagine that's your close jipping. So 1, 4. So what we have, you will have a tuple. 1, 4, 2, 5, 3, 6. Yeah, okay. Yeah, we take one element from each. Yeah, we jip it. Yeah, look, jip it. Okay. Okay, so now there's another way of doing that is that we can use the jip function, but a little bit special here. So instead of jip, we put a star here, jip m. Okay, here. So look here, 1, 2, 3, 3, 4, 1, 2, 2, 3, 4. So when I jip this, and I convert it to a list, because this thing returns an iterator. If I convert it to a list, then it will give me what? It will give me, and then you can tell me what it is, okay? You will tell me what it is. You will tell me it's 1, 3, 2, 3, 2, 1, 3, 3, 2, 1. Okay, yeah? So what it is? What it is? From here to here, what happened? Come on. This is metric, and if we jip it star list, what do we get here? We have learned this before, right? Look, 1, 2, 3. What happened from this M to the transition to this?
It's just turn.
Yeah, and what's that thing called? We call it. We have learned this before. Remember? We call it transpose. Yeah, we learned this. Yeah, transpose. This is what transpose metric. Okay, so it's like that. So to be more precisely, why these will give the transpose? So for example, this A equals like that. Okay, so that's 1, 2, okay, 3, 4, and then 5, 6. Okay, so what's this? What's the so it's a metric of 1, 2, 3, 4, 5, 6. Okay, so this is the 3 times 2 metric. So if we transpose it, if we do this list jip star A, so what is it? What do we have? So you will have what? You will take 1 from each one, 1, 3, 5. So it will be 1, 3, 5, and then 2, 4, 6. Okay, 2, 4, 6. So look, these elements, each element is a tuple, but it's an array of tuples. So basically, this is kind of like 1, 3, 5, 2, 4, 6. Okay, so look, 1, 2, 3, 4, 5, 6. If we transpose this, look, 1, 2, 3, 4, 5, 6. If transpose this, it will become 1, 3, 5, 2, 4, 6. How do we get it? Look, 1, 2, 3, 4, 5, 6. So we take one element from each. Okay, so look, 1, I take 1 from the first one. Yeah. 3 for the second one, 5 from the third one, so it's 1, 3, 5. Yeah. Second, 2, 4, 6. Got it? That's what it calls transpose. So if we do this, what happens? Now we can transpose it, and then look, if we go through the rows again, and these will be the columns of the original metric, right? So we can check if this is the 1 to n. Am I right? Yeah? Make sense? Okay, so then we can do this. Look. Okay, let's write it, okay? Okay. Define, let's say, check. And if this is a metric, and first of all, I want to get the length, the number of rows. And I can say, and then I need to construct a set of 1 to n, okay? So that's the n, 1 to n, let's say v equals, I want to convert it to a set, and then I will have a range, start from 1 to n, right? Okay, so this is the set of the 1, 2, 3. And then I just need to compare for r in n. If Okay, if R not equal, okay, so look, R is a list. I need to convert it to a set. R not equal V, then we return false. Right? We are checking the rows. Right? We can. And then I need to do this for R in zip star M, transpose it. When we transpose it, the rows will become, these rows will become original, will be original, the columns, right? So, and I can say if set R not equal V, return false, right? Yeah? This is checking the rows, this is checking the columns. And if we all finish the check, if at this point we return what? Return what? Sorry? True, yes. What's the time complexity? What's the time complexity? This is, there are n square numbers here. We need to compare. Yeah? So what's that? Let's say comparing the set. Oh, n square, yeah. Let's say we comparing the sets is constant time, okay? Is it constant time? Yeah, no, it's not constant time, but it's O(n) time. Look, this is n, this is n. Yeah, this is n, this is n. So, okay, so transpose it, we do it one time thing, so it's actually O(n) square, right? Transpose will be another O(n) square plus n square. So it's O(n) square times 2 is O(n) square, okay? Okay, so this is one way of doing. Another way, okay, which in might not find it simple to implement, but let me just explain what kind of argument can we use to compare the equality, right? So what's this XOR? Remember? Do you still remember? Exclusive OR. Yeah, and or exclusive OR. Remember? Remember the tables. And let's write this table. Okay. 1 0 1 0. If this is OR, 1 or 1 is 1. 1 or 0 is 1. 0 or 1 is 1. 0 or 0 is 0. Yeah? One of them is true. If this is n, 1 and 1 is true. All others are false, right? Yeah? So this will become, yeah? Alright? Eric and Ryan needs to do work. So that's two things. One Eric do it, Ryan didn't do it, then that's false, okay?
Yeah.
And now how about if Eric or Ryan, so one of them is true, then it's true, right? How about exclusive OR? Remember, 1 1 is 0, 0 0 is 0, 1 0 is 1, 0 1 is 1. Okay, so can you tell me what's exclusive OR?
If it says if they both are the same, then it's false, and if it
Otherwise, it's true, yeah?
Yeah.
Okay, let's see. Exclusive OR, yeah, exactly. So it has to be, both has to be different to be the same, to be one, okay? Okay, so look, we are checking. We want to check if each row is contains the number 1 to n, right? And how about if I know, because 1 to n, I can exclusive 1, exclusive 2, exclusive 3, till exclusive n, right? Yeah? If I say this is x, right? And then if I exclusive all the numbers again, this x, okay, so can you tell me if I use this x to exclusive 1, 2, 3, what happened? If I look, it's s exclusive 1, exclusive 2, exclusive 3, exclusive till n. So what's this value? What's this value? Come on, x is 1 exclusive or exclusive 3 exclusive till n. And then I use add these x values to exclusive 1 again, exclusive 2, exclusive 3, exclusive 4 until exclusive n. So what's this value? What's the value? Come on. So what does it mean? X equals this, then it means that 1 exclusive 1, 2, and then exclusive 1 again. Yeah? So 1 exclusive 1 equals what?
1 exclusive 1 equals 1, no, 0.
0. 2 exclusive 2. If it's the same.
0.
3 exclusive 3.
0.
Okay, so x exclusive this whole thing. What's the value?
0.
0. Yeah, you see? Because x is 1 exclusive or 2 to n. And then I exclusive 1 again to 2 to n again. So basically I exclusive the same number twice. Right? So that's the important property. If a number is exclusive itself, it'll be 0. It's like an eraser, yeah? Eraser. The same number exclusive itself and then it makes it gone. Okay? Yeah? So I can calculate this value x, obviously. And then I use this value to do what? To exclusive. Yeah? Exclusive all the numbers in the rows. And that must be 0. And I need to exclusive all the numbers in the columns. And that must be 0. Right? Yeah? Any questions so far? I mean, do you understand this approach? Everyone?
Yeah.
So why this will work?
Because,
2 noise, yeah. Right? Look. 1 exclusive, x exclusive 1, exclusive 2, exclusive 3.
0.
That should be 0, exactly. If this is not 0, this row does not contain the numbers from 1 to 3, okay? Yeah? Okay, so let me write it, okay? Could be quicker. Okay, let's say define check metric. And then I can say x equals 0, and I can say for I in range, I start from 1 to, okay, so let's say here will be n equals length n, okay? n plus 1, x exclusive. Okay, so this symbol, yeah, you see, up arrow, it's on the number 6, okay, number 6 key. Okay, you press the shift 6, it will give you this, that's the exclusive equals I, okay. Now we have x. And then now I just need to do what? For R in range n. This is the row index. For C in range n. This is the column index, right? But for each one I have to do this, let's say R equals x, CC equals x, and then I just need to exclusive these, okay? So then RR exclusive equals metric RC, and then CC exclusive metric CR, okay? This is the, okay, so look, I exclusive metric RC, and then metric CR is this one, right? It's mapped along the diagonal, okay? Here, this is metric RC. This one, metric CR. This is metric. Okay, so look. How can we access this number 3? Metric 0, 2. And what's this? What's this? Where is this place?
Metric 0, 3.
No. This is 0, 2. And what's this? Come on.
3.
Why is this 3? 2, 2, 0. So look, RC. If this is metric RC, right? Come on. Listen to me. Metric RC is here. If it's map, oh, this is diagonal. And this place is metric CR. Okay?
That's RC.
I know. Makes sense. Because look, where is these two locations? MRC and MCR.
They're like symmetry.
Yeah, symmetry along the diagonal. Yeah, that's what I'm saying. Yeah. RR. I want to exclusive all the numbers in the rows by RC. I want to exclusive all the numbers in the column by CR. Okay, and then here I should say if RR or CC, if one of them is not 0, then we return false, right? And then otherwise here return true. RR or CC, means that R bigger than 1 or CC bigger than 1. Or we can do this. Max RR CC.
Still small.
If the maximum of these two numbers is bigger than 0, what does it mean? It means that one of them is bigger than 0. Right? If one of them is bigger than 0, it means what? It means that either one row does not contain all the numbers from 1 to n. Or the column does not contain all the numbers from 1 to n. What? Yeah? If it contains from all the numbers from 1 to n, what it mean? The exclusive result, it should be 0. Why is that? Because we are exclusive the same number twice, right? Okay, I'm going to give another mathematical question. Okay, 2 exclusive 3 exclusive 4 exclusive 3 exclusive 2 exclusive 4. What's the answer?
0.
Yeah, because the 2 twice, 4 twice, 3 twice. Yeah, if we exclusive something twice, 0. Like eraser. Yeah. 3. This eraser is 3. I'm exclusive this place. Gone. Yeah? Okay, make sense? Here is Eric. Eric is here. Eric?
Yeah.
Exclusive Eric.
And
Go
I
on.
want to play TV.
Okay. What's the time complexity here?
Oh,
What's the time complexity? Come on, look at this. We are going through the metric. Yeah?
yeah.
So what's the time complexity? Sorry?
N.
N is here. So what's the time complexity?
N cubic.
Why is cubic? Why is the cubic?
Because you did the raise 3 times.
No, only 2.
Square.
N square. Look, why is N cubic? Look, this is N, right? Obviously. N, yeah? N, and that's it. So that's N square. N square plus N, what's the outcome? Which one is bigger?
N square.
N square plus N. We drop the smaller part. So we keep the most time consuming part, okay? N square. It's the same thing as here, just different approach. Okay, so tell me, to sum up, what have you learned so far today?
About the matrix.
Yeah, what are we doing with the metric?
We are doing a Sudoku thingy. Trying to
Uh.
see if they have the numbers in.
From each row and each column should have all the numbers from 1 to n, right?
Mhm.
Okay, so how can we do this? What have you learned today, Eric, Lion? How can we do it? Which approach you think is better? You can remember.
I can't remember
They're
any
all
of them.
Sorry?
They're all very, very, very long.
I can't remember
Very,
them
yeah.
all.
That's fine, but do you know the principle? I mean, so for this approach, we are
It's been
comparing.
22 minutes.
Yeah, we are comparing the set. Yeah, alright. And this one we are exclusive. Because we already know that each one this can be computed. Yeah, from exclusive 1 to n, and then yeah we have a eraser containing the result of 1 exclusive 2 exclusive 3 exclusive till n, and then I use this eraser to rub it.
Oh yeah.
Yeah, that's how it works. Yeah, and then if nothing left is 0, right? Then it's the 1 to n, right? Yeah, make sense? Eric, right? Come on, anybody? Yeah. Okay, so what have you learned today so far? Come on.
Matrix.
Yeah.
What metric?
Is
Transpose.
with only 1 to n.
Yeah, 1 to n.
Numbers in
And how do we
X3.
transpose the metric? Remember the
Using
magic?
set.
No, the transpose. What's transpose?
You do each row and you zip it.
Zip it. Okay, zip it.
Zip it up.
And there's a star here. Yeah? Zip star M to turn it 90 degrees. Okay, transpose is it 90 degrees? Look, this one. It will be, when I transpose this, it will become what? 135, 135, 246. Is it turning clockwise 90 degrees?
Yeah.
No, not really. Because if you turn it not clockwise, it will be 531. So it's not quite a 90 degrees. So how do you turn this to here? You
Mirror it.
You
You mirror it and turn it 90 degrees.
mirror it, yeah, and turn it 90 degrees. Yeah, mirror it will be 2, 1, 4, 3, 6, 5, and then turn it 90 degrees that way,
Yeah.
Anti-clockwise. Yeah, okay. Next called transpose. So basically, it's easy. You just take one element from each, 1, 3, 5, and then take second element, 2, 4, 6. Yeah. Okay, that'll be it today. Bye bye.
Bye.